A bridge is not just steel and concrete. It is a promise that the physics holds, that the engineers got it right, that the structure will still be standing when you reach the other side. Most of the time, that promise is kept. But sometimes, it isn't. And when a bridge fails, it doesn't just fall. It reveals something. A flaw in the design. A flaw in the inspection. A flaw in how much we trusted our own calculations. Today, we're going to look at the deadliest bridge collapses in recorded history. Not just the disasters themselves, but the engineering failures that caused them, the physics that couldn't be ignored, and what the world learned, sometimes too late. Let's start with one of the most studied engineering failures of the 20th century, the Tacoma Narrows Bridge, Washington State, United States. November 7th, 1940. The bridge had only been open for 4 months. It was considered a modern marvel. Slender, elegant, economical. Its main span stretched 2,850 feet across the Puget Sound. Engineers had built it unusually thin for its size. The deck was only 39 feet wide, far narrower than earlier suspension bridges, and that decision would prove catastrophic. On the morning of the collapse, winds were blowing at around 42 miles per hour. Nothing extraordinary. But the bridge began to twist. Not just sway, twist. The deck would rotate up to 45 degrees on one side, while the other side dropped. Drivers had reported strange undulations in the weeks before. Some found it thrilling. Engineers were aware of the oscillation, but considered it manageable. They were wrong. The physics at work was aeroelastic flutter. When wind moves across a flat deck, it creates pressure differences above and below the surface. At certain wind speeds, those pressure differences begin to synchronize with the bridge's natural frequency. The structure starts to feed energy back into its own oscillation. Each cycle amplifies the next. Eventually, the twisting overwhelms the structural integrity of the cables and deck. At 11 a.m., a key suspender cable snapped. A 600-foot section of the deck tore free and fell into the water below. One person was on the bridge when it failed, a reporter named Leonard Coatsworth. He crawled to safety on his hands and knees. His car and his Cocker Spaniel went down with the bridge. Amazingly, no human lives were lost at Tacoma Narrows, but the failure changed bridge engineering forever. Wind tunnel testing became standard practice. Aerodynamic deck profiles replaced flat sections. Every suspension bridge built after 1940 owes a design debt to what failed here. If you're finding this breakdown of bridge engineering history useful, consider subscribing to Next Build. We cover the physics, logistics, and scale behind the infrastructure that shapes the modern world. New videos every week. Now let's move to a failure with a far more devastating human cost. The Quebec Bridge, Canada, August 29, 1907. The Quebec Bridge was being built across the St. Lawrence River. When complete, it was designed to be the longest cantilever bridge in the world, a span of 1,800 feet, an extraordinary engineering ambition for the early 20th century. Cantilever construction works by building outward from both sides of a central pier. Two arms extend in opposite directions, balanced against each other. When they meet in the middle, the span is complete. On the afternoon of August 29th, workers on the south cantilever arm noticed something alarming. Steel members near the base were buckling, bending out of shape. Supervisors on site were told. Work continued anyway. At 5:17 p.m., the entire south arm collapsed. 86 workers were killed. Many of them were Mohawk ironworkers from the Kanawake community, families who had sent multiple members to work that day. the investigation revealed the fundamental cause. The lead engineer, Theodore Cooper, had authorized an increase in the bridge's total weight without recalculating the stresses on the existing steel. The lower cord members, the main compression members at the base of the cantilever, were simply not strong enough to carry the revised load. They buckled, and the entire structure came down in 15 seconds. But the story doesn't end there. The Quebec Bridge was redesigned, a new structure was built, and on September 11, 1916, during the lift of the central span, the cast steel lifting mechanism failed. The center section fell into the river. 13 more workers died. The Quebec Bridge finally opened in 1917. After a decade of construction, 2 catastrophic collapses, and nearly 100 lives lost. It remains one of the most tragic engineering sagas in North American history. The failure at Quebec exposed a systemic problem that would reappear in disasters for the next century: the gap between calculation and verification. Engineers would design something bold. Contractors would make changes under cost or schedule pressure, and the updated stresses were never fully rechecked. This pattern appears again and again in the Silver Bridge, in the Fider Bridge, in disasters on nearly every continent. Let's talk about the Silver Bridge collapse. Point Pleasant, West Virginia, December 15th, 1967. The Silver Bridge connected West Virginia and Ohio across the Ohio River. It was an I-bar chain suspension bridge, a design that was already considered unusual by 1967. I-bar chains work differently from conventional wire cable suspension. Instead of bundled steel wires carrying tension, the bridge used interlocking steel bars, each with an eye at each end, linked like an enormous chain. The entire load of the bridge hung from those chains. There was no redundancy. If one link failed, the whole chain failed. At 5 p.m. on December 15th, the bridge was carrying its normal load of rush hour traffic. 37 vehicles on the deck. Then a single I-bar fractured. The crack had been growing for years. A stress corrosion crack, just 0.1 inches deep, invisible to visual inspection. The crack originated at a manufacturing defect in the steel, a slightly flawed pit in the eye of one bar over millions of load cycles. The crack slowly propagated through the metal until the bar could no longer hold the stress. In less than a minute, the entire bridge collapsed into the Ohio River. 46 people died. 1967 was a turning point for infrastructure inspection in the United States. The Silver Bridge failure led directly to the creation of the National Bridge Inspection Program. Every bridge in the country required systematic structural inspection on a regular cycle, a practice that remains law today. The lesson was clear. A bridge is not a static object. It is a dynamic structure under constant stress. And microscopic flaws, invisible to the eye, can be just as deadly as gross structural failure. Now we travel to Europe, Germany, 1983. The Reichsbrücke in Vienna had actually already collapsed once before, in 1976. But one of the most instructive European failures of the century occurred over the Rhine, the Zeulenroda Bridge, and more famously, the collapse that shocked the engineering world in 2007, the I-35W Mississippi River Bridge in Minneapolis, August 1st, 2007. The I-35W bridge carried approximately 100,000 vehicles every day. It was a critical artery through the heart of Minneapolis. At 6:05 p.m. during evening rush hour, the bridge collapsed. 13 people were killed, 145 injured. The investigation took months. The cause was eventually traced to undersized gusset plates, the flat steel connection plates that join structural members at a bridge's nodes. The original design from 1961 had specified gusset plates that were inadequate for the actual loads on the bridge. The error was in the original design documents, and it had never been caught. For 40 years, every heavy truck, every load of construction equipment, every expansion in traffic volume was pushing those gusset plates closer to their failure point. On the day of the collapse, a construction project on the deck had added additional weight. Approximately 280 tons of construction equipment and material were positioned over the weakest section of the bridge. That was the final increment. The gusset plates yielded, and the bridge fell into the Mississippi River. The I-35W collapse triggered a national audit of structurally deficient bridges across the United States. Thousands of bridges were flagged for review or repair. It also accelerated the adoption of structural health monitoring technology, embedded sensors that measure real-time stress, vibration, and deformation inside bridge components. The kind of monitoring that gives engineers early warning before a crack becomes a catastrophe. We should also look beyond North America, because some of the world's deadliest bridge collapses have occurred in places where engineering oversight and material quality were far less regulated. The Hyderabad Bridge collapse, the Mahad Bridge collapse in India, 2019, and most devastating of all, the Hyderabad Bridge in Senegal. But perhaps the single deadliest bridge disaster in recorded history occurred in India. The Mahad Bridge over the Savitri River, 1994. A colonial-era bridge built by the British in 1922. On the night of July 26th, flash flooding from Cyclone Esta struck the Savitri River. The river rose faster than anyone anticipated. A passenger bus crossed onto the bridge, then another. At the moment of crossing, the bridge, already weakened by decades of monsoon flooding, simply gave way. 2 buses and several cars plunged into the swollen river. At least 45 people were killed. Many bodies were never recovered. The bridge had been flagged for poor condition. Repair budgets had not been allocated, and the pattern repeats. Knowledge of the risk, inaction on the warning, and then catastrophe. Let's move to one of the most recent and painful examples, the Morbi Bridge collapse in India, October 30th, 2022. The Julto Pul suspension bridge in Morbi, Gujarat, had just reopened after renovation. It was a historical pedestrian bridge more than a century old, spanning the Machu River. The renovation had been completed. The bridge had been reopened to the public just 5 days earlier. No load testing had been conducted. No official safety certification had been issued. On the evening of October 30th, the bridge was crowded with visitors, holiday crowds, families out on a Sunday evening. An estimated 500 people were on the structure when it failed. The pedestrian cables snapped. The deck fell into the river. At least 135 people were killed, many of them children. The failure was later linked to the use of substandard materials during the renovation. The cables showed signs of severe corrosion. The renovation contractor had no engineering license, and the municipal authority had issued no safety inspection before reopening. This is not a failure of physics. It is a failure of process, of governance, of the systems that are supposed to stand between an aging structure and the public who trusts it. So, what connects all of these collapses? The physics changes, the locations change, the eras change, but the underlying failure pattern is remarkably consistent. A structure was stressed beyond what it was designed to carry, or it was designed with an error that was never caught, or it deteriorated in ways that were not monitored, or it was rushed back into service without verification. Bridge engineering has made extraordinary advances since 1940. Finite element analysis allows engineers to model every member of a structure under thousands of simulated load conditions. High-strength weathering steels resist corrosion far better than their predecessors. Structural health monitoring systems can detect microvibrations that signal developing fatigue cracks. And yet, the world's infrastructure is aging. In the United States alone, approximately 42,000 bridges are currently classified as structurally deficient. In Europe, large portions of the motorway bridge network were built in the 1960s and 70s. They were designed for a 50-year lifespan. Many are now past it. In the developing world, colonial-era bridges still carry loads they were never designed for. The engineering knowledge exists to prevent every type of failure we have discussed today. The gap is not in the physics. The gap is in the investment, the inspection, the political will to spend on infrastructure before it fails rather than after. There is a concept in structural engineering called the factor of safety. When engineers design a bridge, they do not design it to carry exactly the load they expect. They design it to carry several times that load. The factor of safety is the margin between what a structure is expected to carry and what it would take to make it fail. For most bridges, that factor is between 2 and 4. It is the built-in buffer against miscalculation, against unexpected loads, against materials that are slightly weaker than specified, against a design error that slips through. But factors of safety are not permanent. They erode. Every time a truck heavier than the design limit crosses a bridge, the factor decreases fractionally. Every winter of freeze-thaw cycles works microfractures deeper into the concrete. Every year of deferred maintenance narrows the margin until one day, the margin is gone, and what was designed to hold holds no longer. The bridges that fell were not always poorly designed. Some of them were remarkable achievements for their time. What failed was our understanding of how structures age, how flaws propagate, how the gap between inspection and reality can grow silently for decades. The engineering lessons from each of these disasters became code, literally. The Tacoma Narrows failure rewrote how suspension bridges handle wind loads. The Silver Bridge failure created national bridge inspection law. The I-35W collapse accelerated structural health monitoring technology. Every update to bridge design standards in the United States, in Europe, in Japan, in Australia, carries traces of a disaster that happened somewhere in the past. The building codes we follow today are written in the losses of the ones we didn't. That is how engineering progresses, not only through inspiration, but through failure, through the painful, meticulous process of understanding what went wrong and ensuring the next generation of structures carries those lessons forward in steel and concrete. The next time you drive across a bridge, it might be worth thinking about what you're crossing. Not just the physical structure, but the accumulated knowledge of every bridge that fell before it. The engineers who studied those failures. The inspectors who run their hands along the cables and peer into the joints twice a year. The standards writers who took a catastrophe and turned it into a code requirement. Bridges are not just infrastructure, they are the ongoing conversation between human ambition and physical reality, and that conversation never ends. If you found this deep dive into bridge engineering and infrastructure failure worth your time, subscribe to Next Build. We explore the mega projects, engineering systems, and infrastructure that define the modern world. Drop a comment below. Which collapse surprised you most, and what you think should be done about aging infrastructure. And if you want to keep going, our video on the engineering behind the world's longest suspension bridges is a natural next step. The link is on your screen now. We'll see you there. l'inspiration vient par ce cœur.